Swayam Prabha. Digital India. Educated India.
So, hello students, welcome to another lecture of this course, Thermal and Statistical Physics. So far what we have done is we have started with what is known as kinetic theory of gases, where we are assuming matter to be made up of identical many number of molecules, and we are working under the approximation that there is no interaction between these molecules. So, the only source of energy is kinetic energy, which takes us to the regime of gases, right. So, therefore, we call it kinetic theory of gases, and we have done a great deal on it. We have actually measured the pressure exerted by such an ideal gas on the confinement on the container walls. We have also understood the interpretation of temperature in this formulation, and in the last class we also derived the velocity distribution, the speed distribution of gas molecules when we are dealing with the collection of these molecules. Okay, so if I can quickly recap. So, last time we derived what is known as Maxwell's distribution of molecular speeds, Maxwell's distribution of molecular speed, right, and we derived an expression which looked like this: f of v, which is dnv divided by dv, and this is equal to 4 pi n times m divided by 2 pi kBt raised to the power 3 by 2 times v squared exponential of minus mv squared divided by 2 kBt, right. So, this is what we derived, and basically what it tells us is, okay, so if I and we also plotted it in the last class, maybe I can okay, so this is how it typically looks like. So, if I put Fv on the y axis and V on the x axis, since there is a contribution of V squared in the beginning, right, at small, so say this is 0. So, if this is 0, then initially it increases by the functional form V squared, but at higher V's the exponential term takes over and it decays, right. So, it typically looks something like this, all right, and it decays exponentially. And one thing, and also like we saw, so basically it is telling us how many molecules are moving with velocity v in a window of dv, right. So, if I take dv to the right hand side, this gives me the number of molecules that are moving between speed v and v plus dv, all right. And one way to do that is just to make a small slice of this plot, right, and calculate the area under this part of the curve, and that will tell you how many molecules are moving with velocity or speed v within a window dv, right. So, this number basically is d of nv. Okay. So, this is what we saw in the last class, all right. And another other important things to consider or to pay attention to here is that f of v only depends upon mass m, right, mass and temperature T, right. So, these are the only independent, these are the only properties of the gas that goes into this expression. The one is the mass of the gas molecule and other is the temperature of the gas, right. And in fact, if we in fact we can learn more about more from this expression. So, if I plot okay, so I will do this plot again slightly bigger, okay, f of v. But now what I will do is I'll plot this f of v for 3 typical temperatures, right. So, let's use 3 colors perhaps. So, okay, so the blue, let's say blue, there is one blue, okay, so it starts from 0, remember. So, we can do another maybe yellow, and the third one we can maybe do red. And the way these 3 curves differ from each other for the same gas is just by the temperature, right. So, if I call this T1 with for the yellow, so for the blue, T2 for yellow, and T3 for red, then clearly we can see that in this case T3 is greater than T2 is greater than T1. Okay. So, all it is telling us is that if we increase the temperature of the gas, the distribution shifts right in the rightwards, right. So, more and more molecules are moving with greater and greater speeds, and that is what we expect, right. So, if we pump energy or temperature into the system, the mean kinetic energy of those gas molecules increases, and that gets reflected in the distribution. All right. All right. So, I hope that is clear. But what we will do next is basically we will use this distribution to evaluate some more important quantities. All right. So, for example, let us see how we can evaluate the average speed of gas molecules. All right. So, average speed. Okay. So, so remember, like we have a distribution and we can evaluate the average of quantities over those distributions. So, very clearly, so the average speed of these gas molecules will be basically equal to integral 0 to infinity v times the distribution of d of n v, right. So, d n v divided by 0 to infinity d n v. So, this is like the number of molecules moving with velocity v multiplied by that velocity divided by total number of gas molecules. So, this is just a standard definition of averaging, and this clearly takes a form. So, the denominator just becomes 1 by n, when n, which is the total number of gas molecules, and this integral becomes 0 to infinity v of d n v, right. And all we will now do is we will just substitute the value of d and v from this expression. Maybe I can write that again. So, so your v average will just become, which implies v average is 1 by n. You just substitute d and v here, and we are left with 4 pi, or maybe I can take it out of the integral already, times. So, all the values which are independent of v, which is this coefficient with this term, that I will just write outside, 4 pi n times m divided by 2 pi k b t raised to the power 3 by 2 and 0 to infinity. So, v times v squared becomes v cube exponential of minus m v squared by 2 k b t dV, right. So, this is what we have to evaluate. And if you remember from the last class, we used this standard form of gamma function. So, which I can write again. So, gamma function, which is defined as follows. Okay, so, it is defined as, so any integral which looks like this, 0 to infinity of v raised to the power n e raised to the power minus b v squared dV, that just takes a form which looks like this, 1 divided by 2 b raised to the power n plus 1 by 2 times gamma of n plus 1 by 2. So, this is the gamma function, right. And clearly you can see here that we are, our n is 3, right. So, therefore, we have to substitute 3 in place of n, and this gamma becomes gamma 3 plus 1 by 2, which is gamma of 2, right. And if you remember and use the value of gamma of 2, which is exactly equal to 1, alright. And if you substitute these numbers in, there is little bit of algebra, could be fairly simple. So, if you do that, we will get, maybe I can write down these intermediate terms, m by 2 pi kbt raised to the power 3 by 2 times 1 by 2 m by 2 kbt squared, and if you simplify this, so this just becomes 8 by pi kbt by m, and this basically just can be written as rounded off to 2.55 kbt divided by m, right. So, this is our final result. So, average speed of a gas molecule at any temperature T is given by this expression, right. So, that is one thing. Another fairly simple thing that we can do is what is known as most probable speed. Okay. And what is most probable speed? That, as the name suggests, from the distribution there is a speed for which the maximum, there are the most maximum number of molecules are moving with that speed, right. So, where the distribution achieves a maximum value, right. So, this we can call as most probable, maybe Vp or something, right. So, the most probable speed of the gas molecule, and as you can see, this is nothing but the maximum of the distribution, right. Maximum of the Maxwell distribution, right. And that simply means where our dFv by dV, the derivative of this distribution, attains a value of 0, right. So, all we have to do is we just have to evaluate the derivative of this expression with respect to V, all right. So, if we do that, so again very fairly straightforward algebra. So we get so maybe I can write down 4 pi n times m by 2 pi kbt raised to the power 3 by 2, that is the term which is independent of V, and you take derivative of the other term which has V dependence, exponential of minus mv squared divided by 2 kbt. Okay. So, I can use the square bracket, okay, and you have to equate this to 0, right, and we have to basically solve this equation for V, right. So, again very simple. So, this basically just drops out, you just have to take derivative of these two terms, and I will just skip the little bit of algebra here, it is fairly straightforward, and what you end up getting is something like this. I have just skipped one step, which you can go home and do it, kbt equal to 0, and we get the, and when we solve this for V, we get the value of velocity which is equal to 2 kbt divided by m, right. And so what it is saying is that for this velocity or for this speed, the distribution achieves maximum, right. So, this is basically V of p that I marked here, right. So, this is the most probable speed with which gas molecules are moving, right. So, this is the most probable speed. Okay. And another straightforward thing that we can do is what is known as energy distribution. Okay. So, remember, so far we have been interested in how many molecules are moving between speeds V and V plus dV, right. But you can also ask a question, how many molecules are moving with kinetic energy E and E plus dE, right. So, how many molecules are there in this window, all right. So basically what we are saying is, what we are interested in is number of molecules between energy E and E plus dE, right. And when we say energy, we are obviously dealing only with the kinetic energy, because potential energy is 0. So, and we can write the energy of the gas molecule as half mv squared, right. And if you, we can just see that in this case, if we take derivative, your dV dE becomes mv dV, and if you substitute the value of V from this relationship, so this just becomes m times square root of 2E by m dV, and this is nothing but 2 me dV, right. So, your dE is basically 2 me dV, all right. So, therefore, we can write dV in this way. So, dV becomes 2 me raised to the power minus 1 by 2 dE, all right. So, we have calculated the differential of velocity in terms of differential of energy, and all we have to do is we basically have to substitute this dV into the Maxwell distribution, right, into the Maxwell distribution. But we are making a very subtle assumption that we are saying, okay, so we are assuming that number of gas molecules between V and V plus dV is exactly equal to number of gas molecules between E and E plus dE, or in terms of notations we can just write d of Nv equals d of Ne. And this is not really an assumption, this is actually a fact, because the kinetic energy is only a function of speed, right, only a function of velocity. So, the number of molecules between V and V plus dV, that is the same number of molecules that are also between kinetic energy E and E plus dE, right. So, so having said that, now we can substitute the value of dV, right. So, therefore, our d of Ne simply becomes, so all I am doing here is I am substituting, I am replacing the velocity or the speed V in terms of E, right. So, our V squared simply becomes V squared becomes 2E by m, okay. And similarly, here I replace V squared by 2E by m, and the dV basically becomes 2 me raised to the power minus half dE, okay. So, that is exactly what I am doing, and if you do that, so okay, maybe I can write down. So, 4 pi n times m divided by 2 pi kBt raised to the power 3 by 2 times 2 E by m times exponential of minus E by kBt times dE divided by 2 me, all right. And if you do little bit of simplification here, so we can write down our final answer, which is f of E. This is now Maxwell energy distribution, okay. So, this becomes d n E by dE, and this is basically equal to 2 n times E by pi raised to the power half times 1 by kBt raised to the power 3 by 2 times exponential of minus E by kBt, all right. And this is basically the energy distribution that we wanted to calculate, all right. And we can also even quickly plot it. So, remember the velocity distribution had a form which was quadratic initially and then decaying exponentially, but here the form is a square root of E, right, and decays exponentially later. So, I can maybe quickly draw. So, your x axis is E, y axis is f of E, and initially this is like square root function which decays exponentially, right. So, this is like square root E initially at small e values, remember this is 0, and later it decays exponentially, right. So, this is how the energy distribution looks like. Okay. So, having done all that, there is also another interesting experimental experiment which was performed almost 100 years ago, which verified this Maxwell distribution. Okay. So, basically I will just talk about experimental verification of Maxwell distribution, speed distribution. Okay. Okay. So, these were experiments that were performed by two I guess gentlemen, Zartman and co. These are two people in the year 1920, and they basically wanted to test or experimentally verify the Maxwell-Boltzmann distribution. Okay. And they did a very clever experiment. All right. So, this goes as follows. So, what they did was, so they took a container. So, I am giving you a very simple picture of it, right, and they used bismuth material, right, and the property of bismuth is that it does not melt. Okay. It directly sublimates into gaseous form. All right. So, you have solid bismuth and it just sublimates. All right. And they added maybe I can use few colors. So, they added a slit. Okay. So, this is a slit. Okay. And since this bismuth is heated a little bit and it is sublimating, so these bismuth molecules, they are in gaseous form and they are sublimating out of this bismuth metal, and what they do is they use a cylinder. All right. So, I am just drawing a side view of this cylinder with something like this. Okay. So, this is a cylinder, a long cylinder, and there is a opening, slight opening at the cylinder. All right. So, there is a tiny slit at the cylinder through which these bismuth molecules can pass through. All right. And there is a plate. Okay. There is a plate on which these bismuth molecules, they get deposited and they leave a mark. All right. So, so it is like they are getting deposited and you can see the deposition with eye, right. So, you can see they get deposited. All right. And what they do is they rotate this cylinder, all right, either clockwise or anti-clockwise, it does not matter, and they open the slit for some time and they close it, right. And therefore, these bismuth molecules, they are moving up with certain speed, right. And like we now know that there is a distribution of these molecules with which they are moving up, right. And what happens is that the faster molecules, okay. So, remember the kind of distribution we are dealing with. So, we have a distribution where some molecules are moving really quickly and other molecules are moving relatively slower, but there are large number of molecules and there are few molecules which are very, very slow, right. So, therefore, now I want you to use your imagination. So, the faster molecules will get deposited first, the slower molecules will get deposited later, and since this cylinder is rotating, they will basically get deposited and which will reflect the underlying velocity speed distribution. All right. So, what they later do is they remove this plate, right. So, I am just now drawing this plate. So, this is the plate. Okay. So, they remove this plate and what they observe, maybe I can use red color. So, so there are very few molecules which arrived very, very late, okay, but there were some molecules or atoms rather, right, because these are bismuth atoms which got deposited, and then there were fewer and fewer atoms, right. Okay. And what they did was they basically plotted the quantity they observed the amount of atoms deposited on this plate, right, which can be characterized either by the how much the plate has blackened, right. So, maybe I can write blackening of plate, right, and this is the position, right, from 0. So, this is where the first atom got deposited, which was the fastest atom, and then there was the slowest atom which got deposited, and beyond that there was no atom, right. And when they plotted this blackening of the plate as a function of this position of the plate, right. So, this is position. So, what they observed, so their data points looked something like that. Maybe I should be okay. So this is where the peak was, okay, and then it decayed. Okay, so these were the data points, all right, and this is basically the position along the plate, right. And again, like, just imagine how this experiment is going on. So, the fastest molecules, they got deposited the earliest, and they corresponded to the position which was far right, right. Remember, the plate is going, the cylinder is moving like this, and when they fitted this data with this expression, which is the Maxwell distribution, okay. So that is the fit. Maybe I can use the blue color. Okay, so basically the black cross is experiments, and the blue line is the Maxwell distribution, speed distribution. Okay. So, this was a really nice experiment with which they could verify the Maxwell-Boltzmann distribution, all right. Okay. So, we will switch gears a little bit, and we will start a relatively different topic, basically just to highlight one thing which we have been ignoring so far, all right. So, let us talk about mean free path of gas molecules. Okay, so what is mean free path? Okay. So, I will start by giving you again a very simple example that again we encounter all the time. So, say we are sitting in a classroom, right. So, let me draw some classroom, right. So, let us say this is the classroom, and the classroom has dimensions of the order, like, let us just assume it is like 10 meters, right. Okay. And let us say somebody opens a bottle of perfume at one corner, right. Okay. And of course, these perfume molecules, they are like in a vapor phase, they are like a gas. So, they travel from one corner of the room to the other corner, right. And and we can so the question that we are so what we can do now is we can estimate how long will it take for these perfume molecules to go from one corner to the other corner, right. So remember, like in the last, like, first or second lecture, we saw that the typical speed with which these gas molecules are moving in the air is of the order of hundreds of meter per second, right. Right. We saw that for hydrogen this value is very high, like thousands, but since perfume is typically an organic molecule, it is quite heavy. So, we are assuming that it is very slow, it moves very sluggishly, but still that velocity will be of the order of 100 meters per second, right. And also the distance this molecule is going to move from one corner to the other is like of the order of 10 meter, right. So, distance traveled is of the order of 10 meters, right. So, from these two numbers we can very easily estimate. So, the time it will take for the smell of the perfume to travel to the other corner. So, that will be basically distance divided by speed, right, 100. So, this is like 0.1 second. Okay. And from our daily observations, we know that this is not true, right. It takes much longer for smell to go from one corner to the other, right. So, what is going on, right. So, we have to figure out what really goes wrong. Okay, so I can maybe I can say that in reality it takes much longer than 0.1 second, right. It usually takes of the order of 10 even more seconds, right. So, let us see what goes on, right. So, okay, so maybe we can directly go to the reason. So, we already know, right. So far we have been assuming the gas molecules, they are dimensionless, they are point like, they do not really collide with each other, they are only colliding with the container walls, the boundaries of the container. But you know, that is not really true, right. So, gas molecules, they do have finite dimensions, they do undergo collisions among each other. Okay. So, therefore, the trajectory that a typical perfume molecule will take from one corner to the other is not a straight line, right. So, here we assume that the molecule is moving without any hindrance in a straight line and it is taking 0.1 second, but that is clearly not true, right. So, in reality, say you start from point A and this is say your gas molecule that we are tracking, there are many more gas molecules in its path, right. So, maybe many more gas molecules. So, say it is going to point B. So, rather than going straight, what it does is it moves, it gets collision from other molecules, right. It undergoes multiple collisions and so on, right, and only then it can even go backwards after colliding and only then it goes to the point B, all right. So, therefore, the length, the distance between point A and B is not L, but it is much greater than L, because the actual trajectory of the gas molecule is quite zigzag, right. So, it is actually travelling lot more distance than we earlier estimated here in this calculation, all right. So, therefore, so maybe I can write down. So, actual trajectory of the gas molecules of the gas molecule is zigzag, right, zigzag rather than a straight line. Okay. So, therefore, it is travelling much greater distances than L. Okay. So, basically the underlying fact is that this molecule is undergoing various collisions while it travels in the medium, right. And now we can define a quantity called lambda. Okay. So, let us say the molecule starts from this point, it moves along a straight line over a distance say lambda 1 before it undergoes a collision. After collision, let us say it again travels a distance lambda 2 and undergoes another collision and so on, right. And we can define a quantity which is known as mean free path. Okay. And what is mean free path? So, this is basically average distance travelled by a molecule between two successive collisions. Okay. So, this is basically the average of all these lambdas, right. So, how long how far a gas molecule moves before undergoing another collision, right. So, that is what mean free path is, all right. So, this is typically denoted by symbol lambda, okay. And again, like we can now write down the definition. So, say say n is the total number of collisions between point A and B right, and the total and lambda 1 plus lambda 2 so on plus lambda n is the total distance travelled by the gas molecule. Okay. So, therefore, clearly we can write down the lambda as follows. So, this is just total distance travelled divided by total number of collisions, right. So, this is a simple definition of the mean free path, right. So say okay. So, let average speed of gas molecule, or I can just write molecule of the molecule. So, let us say this is V average, okay. Then what will be the total distance travelled, right. So, in that case we can just write it V times T divided by N, where T is total time taken total time taken between by molecule between A and B, right. So, we can just write our lambda in this way, okay. And we can even define another quantity. So, so we can also write so lambda, which is I just wrote V average time T divided by N. So, I can define this as V average times tau, where tau is known as mean time between two collisions, right. So, basically what I am saying is it took time t to go from point A to point B, and there were n number of collisions that this gas molecule underwent. So, therefore, the mean time between two collision is just n t divided by n, right. So, that is just V of tau, right, that is what I have written. Okay. So, now let us see if we can okay. So, remember this lambda is expressed in terms of average speed and tau, which is something which is not, we can't really calculate, right. So, this is like mean time between two collisions. So, let us see if we can find an expression for lambda. Okay. So, again we have to use our imagination now. So, what do we really mean by the term collision, right. So, say our gas, so let us assume our gas molecules are just, they look like spheres of radius r, right. Okay. So, say this is a gas molecule, it has a radius r, and if there is another gas molecule, okay. So, let me, so say there is another gas molecule which also has radius r, and if the centers of these gas molecules if the centers of these gas molecules, they are closer than a distance of 2 r, then they will undergo collision, right. So, you can imagine like if the distance between centers of two gas molecules is less than twice the radius, they will collide, otherwise they will not collide, right. So, basically what I am saying is, so if if maybe I can use a different symbol here. So, let us say this is capital D, this is the distance between the centers of two molecules. So, if D is less than or equal to 2 r, they will collide, we write collision, and if D is greater than 2 r, they will not collide, no collision, right. So, it is like saying every gas molecule is moving with a with some distance associated with it such that if another gas molecule comes within that range, it will undergo a collision, right. So, therefore, you can now imagine, you can clearly see that see like the diameter of the molecule is d, which is basically 2 r. So, if there is another molecule okay, which comes within a whose center comes within a range of d, okay, then they will undergo a collision, otherwise they will not undergo a collision, right. So, what I am saying is um, so there is a okay, so there is a zone associated with every gas molecule which has a thickness d, right, where if there is another gas molecule in that zone, it will undergo a collision, right. So, this is collision zone, all right. So, this is the collision zone. So, okay. So, now remember, so this gas molecule is moving in the medium with the collision zone of d, right. Okay. So, let us say okay. So, remember, so the gas molecule, okay. So, the speed, so the speed of molecule like we saw is basically V average, right, and over a time t, right. So, over a time t, this gas molecule will trace out a volume in the space which looks like a cylinder, right, and whose length is V t, okay, and the radius of that cylinder will be d, right. So, remember, this molecule is moving through the medium. Over a time t, it will move over a distance of V t in a straight line. This is what I have drawn as a cylinder, and the radius of this cylinder would be d, right. And like I said, if there is another gas molecule which comes within the influence or inside this cylinder, that will undergo that will collide with this molecule, right. So, basically maybe I can write down. So, so distance travelled in time t is basically V average time t, right, and this collision zone will now basically look like a cylinder whose length is V t and radius is d, right. Now, let us say that small n is the density of gas, right, which is basically total number of gas molecules. Maybe I can use a different symbol perhaps, or maybe okay. So, this is, maybe I can just write total molecules divided by total volume, right. So, therefore, how many collisions this molecule will undergo in this volume. So, that will be equal to the number of molecules that are inside this volume, right. Okay. So, what is that volume? Okay. So, I can write, so total number of collisions in time t will basically be equal to number of gas molecules inside a volume inside the volume of the cylinder volume, which is basically pi r square h, right. So, r is the d, so this is pi times d square times V times t, right. So, this is the volume, and multiply this by n, that will be the total number of gas molecules inside this volume. Okay. So, therefore, so this is the total number of collisions that this molecule has underwent in time interval t. So, then what will be the collision frequency, right? Collision frequency, and what is collision frequency? That is just the inverse of mean time between two collisions, right. So, that is just 1 by tau. So, this is just 1 by tau, and that is just total number of collisions per unit time. So, that is pi d squared V t n divided by T. So, this is just equal to pi d squared average V times n. So, this is the collision frequency. So, now we can basically substitute this value of tau in the expression for mean free path. So, therefore, lambda, which was equal to average velocity times tau. So, this just becomes so V divided by pi d squared V times n. So, this cancels out and we are left with pi and d squared. Okay. And this is the so this is the so this is the expression for lambda that we were after. Okay. And this is the expression for mean free path. Okay. Okay. So, I forgot to mention. So, in this derivation we basically assumed that the only molecule which is moving is the one which we are keeping track of, and all other molecules in the gas, they are stationary. It is a silly approximation, but that is what we essentially used, right. We just said that we basically map out a volume in space and we just count how many molecules are there in that volume, and that will tell us how many collisions this molecule has undergone, right. But you can do much more accurate calculation with this, right. So, maybe I can write here. So, this expression is assuming only the tracer molecule is moving and other molecules are stationary. Okay, this is important to mention, important to highlight, but we can do better calculation, right. So, we can also do another case. So, we can also consider a situation. So, case 2, let me call it case 2. Okay. So, when medium molecules are also moving with certain average velocity, average speed, and let us assume that is equal to V average, right. So, it is same as the speed with which the tracer particle was moving. So, you can take it as V RMS or V most probable or average speed that we calculated in the class before, it does not really matter. But again, this is also another silly approximation. So, all we are saying is the tracer molecule is also moving with certain speed and all the medium molecules are also moving with the same speed, right. So, I will not really do that calculation. If we consider such a situation, the calculation becomes little bit tedious, but the final result for lambda that we get looks like this. So, 1 divided by 4 by 3 pi d squared n. Okay. So, this is what we get in this situation. And of course, people have done lot more exhaustive calculation as well, which is case 3. So, now you assume that your molecule is moving with certain average speed, but the gas molecules, they actually have the correct distribution, which is the Maxwell distribution. So, when medium molecules have Maxwell distribution, of speeds. Okay. And if we do that calculation, the result is as follows. So, lambda takes the form which looks like this, 1 by square root of 2 pi d squared n. Okay. But you should appreciate the fact that the expression does not really change too much, right. So, here we just had pi. Here the prefactor just changed from 1 to 4 by 3 and here it just changed to square root of 2. So, they are still very similar to each other, alright. So, before we end, we can do one final thing which is the distribution of mean free path. or distribution of free path. Okay, so remember the picture that I drew before. Okay, so what's happening is, as the gas molecule moves through the medium, it undergoes various collisions, and there is a and like we just talked about, we basically calculate the average distance travelled by this molecule between two collisions, right. But now we are interested in what is the typical distribution of these distances, right. What is the distribution of free path between two collisions, all right. So let us get started with that. So, so basically let us assume there is some position, and say we start with a cloud of these gas molecules, right. So, at position certain position, say 0. So, you have n0 number of gas molecules, and they start moving through the medium, right. And like we just saw, that as these molecules they move, they will undergo many collisions, and say after travelling distance x. So, let us say this is x equal to 0, this is x. After travelling distance x, n number of molecules, they avoided collisions, right. So, as we can already imagine, this n has to be less than n0, because if you start with certain number, many molecules will undergo collision, only few will survive, right. And that, say that number after travelling a distance x is n, and say after travelling another incremental distance of dx, that number basically becomes n plus dn, right. So maybe so it's important to see what I am saying. So, say n0 is the number of molecules at x equal to 0. So, n is the number of molecules that avoided collision at x, right, at position x, and n plus dn is the number of molecules that avoided collision at position x plus dx, right. And you can already imagine that this dn has to be negative, right. You can't gain, there is nothing like negative collision, right. So, you will keep losing these molecules. So, dn has to be negative, right. So, dn is negative, or has to be. Okay. So, also we can see that this dn, which is like how many molecules have undergone collision over certain distance, right. So, that dn will be proportional to, so this is the proportionality sign, proportional to the distance that it has travelled, right. So, if a molecule travels greater distances, higher is the probability that it will undergo a collision, right. And also dn is also proportional to the number of molecules you started with, right. So, if we start with many molecules, proportionally equal number of molecules will undergo collision, right. And since dn is and so yeah, so this is what this is, and we can remove the proportionality sign by introducing a proportionality constant, which is minus p times n times dx, right. So, this is how dn varies with respect to these two parameters. Okay. So, where p is a proportionality constant. Okay. So, now we can basically integrate this out. So, we can take n to the other side and integrate this from n0 to n, right. We started with n0, we have n molecules, and so this becomes minus p dx, and this integration goes from 0 to x, right. And if you just solve this, so we have log, so this is log of n, and you compute it between n and n0. So, this becomes log n by n0 log n by n0 is e raised to the power minus px, and if we do this integral, right, so this becomes e raised to the minus px, and finally we get the relationship which looks like this: n equals n0 e raised to the power minus px, right. and let us just define a function f of x which is n divided by n 0, which is equal to e raised to the power minus p x, all right. And what is this? This is basically how many molecules after travelling distance x are there which did not undergo collision divided by total number of molecules that we started with, and this is nothing but probability of avoiding a collision, right. Okay. So, this is what we end up with, but remember here we have a term p which is an unknown constant and we have to evaluate it, right. But now we will use the definition of mean free path. So, okay. So, remember the way we defined mean free path lambda, so which is mean free path, and this is equal to total distance travelled without undergoing collision multiplied by number of molecules that avoided collision divided by total number of gas molecules, right. Okay. So, this is by definition of how we defined mean free path, and this basically just simply becomes 0 to infinity x dn divided by n 0, right. So, this is the distance travelled by these molecules x, right, which did not undergo collision. The integration of dn from 0 to infinity is the total number of gas molecules that avoided collision divided by total number of gas molecules, right. So, this basically just becomes 1 by n 0. So, all I am doing is I am just substituting dn from this equation. So, this becomes 0 to infinity x n 0 e raised to the power minus p x dx, right. And I leave it on you to solve this integral. Basically, you just have to do integration by parts, right. So, these terms cancel out. So, you just do integration by part. And I will just write down the final result. So, you get 1 by p. So, lambda basically we get 1 by p, or even more useful is the proportionality constant that we used is nothing but inverse of lambda, right. So, therefore, the final answer that we have is, so this function f of x which we said is n by n 0 is exponential of minus lambda x, right. And this is basically probability to avoid a collision, okay. And we can also plot it. So, it is a simple exponential function. So, you have f of x and this is x and this just decays exponentially, right, and it decays by a rate which is sorry. So, p is 1 by lambda. So, this should be sorry about that. So, this should be x by lambda, okay. So, this is x by lambda. Okay. So, basically all it tells you is that this distribution of free path is exponential, right. So, there is so it becomes exponentially unlikely for a gas molecule to avoid a collision, right, and the distribution of that path is basically exponential distribution, okay. So, in the next class we will continue with this formulation and we will look at various other macroscopic parameters that we can calculate. Thank you.